So my name's Ty, and hopefully I'm going to explain to you the data journey, our data journey. I think we approached it in a very straightforward way, so hopefully that will come across and you'll understand why we did it the way we did it. But let's go. Okay, so I work for Uniper, but actually I work for a consultancy that is the engineering arm of Uniper. So Uniper was E.ON, and now E.ON have split the company, so we've got two companies. So one is E.ON and one is Uniper. Uniper Technologies, however, is, as I said, it's the engineering arm. So we have specialists all the way from electrical engineering, boilers, gas turbines, performance, steam turbines. My area, which is production solutions, condition monitoring, we've got software teams, we've got a whole raft of people who can help you with things to do with generation. So as I said, my particular team, production solutions, we've got a little sub-team which is called Digital Innovations. And in reality, we are cross-functional because we sit next to all of the engineers doing the day-to-day work, the analysis, the actual engineering. We're a group of physicists, and we just like solving problems, if I'm honest. We actually aim to deliver value. So I think that's the first part along our journey, is we do aim to deliver value. So we very rarely do things that don't progress us along that kind of journey to delivering value. Okay, so we've got systems, and some of those systems are powered by Pi. We, as Uniper, we use all sorts of different components from Pi, but the ones that we generally use and mainly use are ProcessBook, DataLink, servers, obviously, performance equations, and some ACE. But for me, the one that's really important is the SDK. So I said a group of physicists, but actually we do quite a lot of coding, and the SDK makes everything very, very easy. And the new SDK makes things really, really easy. So our universe. So we've got lots of data. As Uniper, we have got Pi servers globally. As E.ON, we had Pi servers globally. We've not just got Pi servers, however, so we've also got lots of vibration boxes. So everything up there that says OV is some kind of online vibration system. All of it's online, so it sends the information back to our servers and our office for our analysts to do the work. But hopefully from there, I kind of got bored at one point and kind of stopped drawing the little circles, but there are a lot of them. And I tried to label as many as I could. But yeah, just hopefully so you can have a bit of a scope of exactly, how big everything is. So my focus is reality. It's very easy to get lost in data and doing clever things with data and using, you hear it all the time, people are doing analytics and they clean some data and they create a model for the data and then they try and do something with the data. Well, for us, a lot of our work is online, so we can't do that in a kind of controlled environment. It's very much the data comes in as it is. It may be good, it may be bad, it may be somewhere in the middle, and we just have to deal with it. So we have to build algorithms that deal with that sort of problem. This particular data set was created by Tom, who's in the audience. This is data from a chimney in Kent, which is, for anyone who's not from England, is in the southeast. It moves in the wind, and this data came out of Pi, but to get it into Pi, we sent it through the cloud, and off the chimney, basically through the cloud, out to Denmark, then back from Denmark all the way back to Nottingham again. This is a real data picture. This is what real data looks like. It's not beautiful. It's got some attributes. It's got some excursions. You may or may not know this sort of data pattern, but in reality, this could be normal, it could not be normal, but without any kind of context, you don't really know. You can see a nice little excursion that goes off on the back. Maybe that's normal. Maybe that happens every time something else happens, but when we're looking at this, we don't know. So more and more of our work is around that problem. So yeah, there's some data. We could model this as some kind of Gaussian shape. We wouldn't be able to adjust for the excursions. We wouldn't understand what the excursions meant. And we could highlight, when things moved around and try and understand it a bit more. But in reality, we need more information to understand this problem. Okay, so I'm going to step ahead. So as I said, our team is cross-functional. One of the main functions of that team is to do vibration monitoring. That's a vibration pattern from a pretty large gas turbine, overlaid with the same vibration pattern for a few different runs. You can see, again, goes all over the place. I like to refer to it as wiggly lines. Sometimes they go up a bit higher than they should do, and maybe we should know about that, and sometimes that's just normal. But again, without context, we don't understand. So we have a system that we refer to as Tiresias. Tiresias has been around for forever, so it's been around for longer than I've been working at the company. Tiresias is our suite of vibration analysis tools that enables us to automatically bring data from all of those little circles from the vibration boxes, put it all into one place, and give us the ability to monitor that data very quickly, and therefore be able to give value back to our customers by not charging lots and lots of money to do the analysis. So back in 2007, we had a bit of a problem. I was an undergraduate at the time, and in fact, it was my first dealing with Pi. So Pi in the company has been around since probably around 2000, but it was kind of held in silos. I think lots of people have talked about this. Initially they get Pi servers on the sites, and the sites eventually realize that they can do stuff with them, and then the engineers get hold of the information. They're like, wow, I can really do something with this because I've got Excel, and we'll do some amazing things. And that's what was happening. So on all the power stations, all this great analysis has been done in Excel, and the guys can use Pi to do it. But as I said, back to context. So vibration data, we've got a pattern here. Let's get rid of the picture in the background. There we go. That we don't really understand. It goes up, it goes down. They're to do with resonance within the turbine. And some of the tracks go a little bit higher than the others, and actually that's to do with context. So there's other signals that cause that, other physical attributes of the system that cause those variations. So my first project, as I said, when I was back in 2007, was the first time that we were really doing anything with Pi. So we thought, well, what we'll do for the first thing is we're going to take some data out of Pi and put it in our Tiresias system. Our Tiresias system was really good for vibration analysis, and what it actually gave us the ability to do was put the context that we needed from the signals that we didn't have access to easily. And it was really simple. And the Pi guys made it really, really simple because I sent them an email saying, what the hell's Pi? And they sent back a load of code that actually enabled me to do absolutely everything that I need to do. So let's take that a bit further. So for that wiggly line, that pattern, there's another problem. How do you map it? How do you map it with context? Well, how do you solve a problem like that? How do you solve it in a way that really works, not just today, but tomorrow and into the future? So we always start off with everything's got to be flexible, everything's got to be scalable. Instrumentation's always rubbish, so instrumentation breaks all the time, and you've got to be able to deal with that. So when mapping vibration signals like that, so that was probably my project in 2008, I've stepped forward a bit, we had to come up with a solution that mapped the wiggly line and brought the context in. For me, always manual, manumatic, automatic are the three golden kind of rules. So whenever you start off with something, you try and do it so that you can work out if it works, then you make it easier, and then you make it super easy. They're my stages. So it turned out that the solution that we came up with, or that I came up with, I guess, was pretty useful. So we called it Spherical, and it enabled us to map data in Tiresias as run-up and run-down. It also enabled us to solve another problem that we were having with clutched gas turbines, steam turbines. If you've ever come across that problem, and it changes the vibration across the shaft line, so you have to understand engagement, but a clutch engagement, but also it changes with temperature. And so we came up with this method that solved that problem. It was flexible, it was scalable. Initially, it was kind of, we uploaded some spreadsheets, we checked out if it worked straight away. Then we just connected to the Tobias server, and then changed everything. So when we connected to the Pi server, we didn't really know what we were looking for. Back in that time, people weren't talking about machine learning and predictive analytics. Analytics wasn't even a word, I don't think. We just called it kind of maths, but just science. And we used the spherical algorithm, as I've just shown it, and that's literally how it works, to map more and more things that were coming out of Pi. So the first thing we used it for was exhaust gas temperatures on gas turbines. And we fed the information live, basically out of Pi into the spherical system, and then used the information that we got out of that and gave it to our gas turbine combustion team, who used it immediately. So we got value out of a system that we basically just created, and then it just spiraled. So we went to Connah's Quay Power Station, which is in Wales, and we talked to their performance engineers, and we worked out that we could build these models, and it was really good. Within 10 weeks, we'd saved Connah's Quay Power Station about £500,000 because of the things that we could find with this system. But our company, they want to, they're a big company and they want to do things in a big way. So when we said that we come up with this idea and that it worked and we plugged it into the Pi system, we've got this, software solution that just seems to work. They say, well, that's all very well and good, but actually there's some guys out in the actual world who say that they've got something better. And we said, okay, right, well, let's see what they've got. If they can do something better than we can, we're not going to stand in their way, we'll just use what they've got. So at Enfield Power Station in 2012, we did a head-to-head trial with this other company, where we did initially it was going to be a 3-month online trial, and then it went out to a 6-month trial, I think. And we did a year blind test of data, so we just downloaded all of the data out of Pi for a year for every single channel, for both of us. And then we had to run it through our respective systems. And it turned out that we were just as good, but actually going back to my beginning statements around what Uniper, as it was Eon Engineering at the time, Uniper Technologies now, what we had was this massive engineering competence. So we were able to outperform this other company just because of our engineering competence as well as our system. So the system was just as good, but the engineering competence was better. That led to a global rollout of both Pi and Spherical. So we started, as I said, in 2012, and it basically didn't stop for 2 years. We were going to power stations all across the Eon, as it was then, Uniper world now, and we implemented this system everywhere because every time we implemented it, we got immediate value back. So whether that be gas, whether that be coal, biomass, wind of all types, hydro and solar, we've tried it on everything, and we always were able to show some value. So going back to Spherical. So we've got this system. We're providing a service from using the system. So it's an algorithm. We've got a load of very clever engineers using the algorithm online plugged into the Pi system. And we're building up lots and lots of failure data. But I didn't really say it, but spherical, I said context, but spherical is an n-dimensional system. So these models, there probably isn't, well, there won't be any models that are identical, not even in our own system, from one unit to another, because the data is always going to be different. Instrumentation is always different. And we are literally building up through developing and delivering our service to our customer this massive failure database. So we thought, wait a minute, we've got this algorithm that is enabling us to determine changes in data that we can identify as failures. Oops, I don't know what's happened there. There we go. We can identify as failures. And we've got all these models for different things that are all different. What is there in those models that is the same? And the biggest problem, and actually the solution to the spherical problem, is normalization. So understanding how to normalize not just data and the way that data moves, but also the metadata that goes around this sort of system. So we started making the models talk to one another. And we've got lots of models. So as I said, we had a global rollout across lots of different countries where everything's, it was quite difficult because everything's in different languages. There's lots of back and forth about interpreting pi tags as this or that. And we started to realize that actually we're creating more and more of this metadata, and this metadata was describing what all this instrumentation was, and the models that it sat in told us more about that instrument than we would otherwise know. And the system was able to, or we were able to build a system that we now call Universe that enabled us to link that together and normalize it, which is a big deal if you've ever dealt with lots and lots of gas turbine type plant, because every single one is different. Every single one. They are not the same. The temperatures that are read from every instrument are different. All of the auxiliary plant is different. But we were able to use all of that information to come up with this ultimately categorizing system that categorized absolutely everything. I think that's the end. Okay, so this is a real trend. It's data from a wind turbine, I think. It's a phase voltage from a wind turbine. So when we look at it, we actually give it an envelope. So this enables our engineers to look at it and work out where things have exceeded and moved away from expected, as it were. So that's what the spherical system does. But actually, it produces this residual. So I've zoomed right in on the residual because it's quite small, so you can see it. This residual pattern is normalized already. So we've got this spherical system that we joined all these things together, and we've got all this data that's coming out of it, that's this residual pattern from this multimodal system, so things that are changing all the time, and they've got n dimensions, but we've got these residual patterns everywhere. And we thought, well, okay, so we've categorized everything so we can, link things together, but we can also do this with the data, and the way we can do it is because we have this normalization capability. Okay, so if you think about what that means, then we've got this residual pattern that's normalized. When it starts changing, as you can see on the left, I've created I've not created, nature created this pattern of what we can now see is a fairly simple data science problem to solve. We've got two lumps on the left, two somewhat Gaussians. The very left peak is actually normal, but the right peak is a growth but it's a residual normalized growth from an n-dimensional system of models that pertains to one particular failure or fault. On the right-hand side is actually what that is, or XY of what that is. There's more dimensions to that particular model, but that's showing pitch control failure, starting to build up on a wind turbine. But the system was able to categorize that from other wind turbines that may or may not have even been from the same site, and identify using normalization methods which data pattern pertained to that pitch problem. But as I said, we've got lots of models. And since 2009, we've been collecting this failure database. And so we've got these residual patterns that are all normalized across all these different models and data, categorization. And when you start linking these things together, you actually have just built something that's pretty much artificially intelligent. So we've got the system that we use every day to provide value every day that connects to our other systems that we use every day to provide value every day. And we feed all that data, that information, that knowledge back into another system that we actually use for our communication to our sites to provide that value. And now we've got a system that actually brings all that together and could probably do it all on its own. What's the problem with that? And that is a problem, actually. So we've got this great idea. It all works. But how do you actually get that information to a human being so that human being believes what it's just been told and can use it? So the first stage of that is to develop things that, as a human being, we can see and understand and access very easily. So on the left-hand side, we've got one of our smart alerts. This has been produced by a kind of offshoot from this system that we're talking about. This enables us to be able to send alerts directly to our customer, and it contains all the information they need to make a decision. That's really important. When you only send part of the information and you expect your customers to go and look at the rest of it, they're not going to do it. Or they're going to prioritize it back because they've got a day job and they're really busy. So by giving them that visualization straight away makes it really easy for them to make an actionable decision. So we've created this, and funnily enough, we just made it work straight off the Pi system. So we've created it for Universe to talk to us through, but in the meantime, it seemed like a really good idea just to hook it up to the Pi system and make it add value straight away. So we did that. So we've got a few guys from Grain Power Station in the audience, and they're getting value from that right now. In fact, that plot there was pretty much created by their analysis. The plot on the right-hand side, on the other hand, is totally different. So the thing on the left is to do with gas turbines, and the thing on the right is from wind turbines. So that's a wind turbine report about ice and being able to pick out ice automatically using neural networks, basically. All this has been created so that we can, at some point, give Universe the voice to start helping us and telling us about failure. At the moment, it's pretty much put to one side, and we use it to help us do our monitoring. So we're still getting value out of it, but until we've solved this problem, being able to give the information directly to our customer in a usable way, that's how we're going to use it, because it's still useful to us. It's our knowledge base. It's helping us do our work and speeding up our work. And once we've got this, then it will be that next stage that I think is pretty much what everyone's looking for. But the way that we built it is around the way that we work, the way that people work, the way that the guys out on site work. And we've actually built this system that is getting smarter as we're getting smarter. As we learn more, the system learns more. And the system can tell us more about the things that we don't see in the data, because it can do this amazing categorization that we couldn't even dream of. Okay, so that's pretty much the end. So Uniper Production Solutions is my team, and we can offer services around gas, coal, biomass, wind, hydro, and solar. And if anyone wants to catch me, then that's me. That's a QR code for my LinkedIn. Please add me and say hello. Thanks.
Thank you. We have any questions for Ty? No modeling?
Thank you, Lee Keane from Entry. I'm curious, you mentioned whenever you deployed your earlier solutions, you always found value. How did you find value on the gas turbine-based plant?
So in reality, we've got lots of data. No one's got time to look at all of it. The very first thing we found on a gas turbine was incorrect function of bleed heat valves that was, under certain condition, was causing the valve to open and drop load by between 10 and 20 megawatts, I think, which is significant. But nobody noticed it. Nobody was actioning it, and because of the way that we'd actually set the system up, we were able to determine that it was the dew point sensor that was causing the issue. So just by using this tool, this anomaly detection system, we were able to highlight that the valve was operating incorrectly and why it was operating incorrectly. So that's one example from a gas turbine. I could literally go on for more than time than we've got, but exhaust gas temperatures, that's a simple one. Losing bits at the back. You're seeing correct heating patterns or patterns that change, and you can identify very quickly what has caused those and what you need to do. If you lose instrumentation that's critical to control systems, the system spots it because the control system is either dealing with it and providing you with a slightly different operation, but we can see that too. Our service is that we send that information straight to the site, and we have a great relationship with our engineers, so that's how we add value. Sorry, as I could keep going on, but I'll stop.
Thank you.
Any more questions? All right, Ty, thank you very much.
Cheers, guys.
Great job.